All right, our final test for the convergence or divergence of a series is called the ratio test. The ratio test has three parts. We will use this again in 9.8, so this is definitely worth absorbing, getting it as well as you can here today. The first piece, the first part to this is right here. The series converges absolutely if the limit as n goes to infinity of a sub n plus 1 over a sub n, the absolute value of that is less than 1. And notice how the little element here on all these limits is the same. So we'll go through this a little quicker. So the second one, if that same limit is bigger than 1, of course that also includes infinity, then the series diverges. And then if you do that same limit and you get 1, then the ratio test is inconclusive, and you got to turn to some other test in order to do that. The ratio test is handy in a lot of scenarios. One of them it's very common if the nth term has some kind of a factorial in it, then the ratio test is quite useful. Okay, so let's take a look at number 1. I'm going to set this up, limit as n goes to infinity of the absolute value what I'm going to do is I'm going to write the n plus 1 term, so that would be 2 to the n plus 1 over n plus 1 factorial. But instead of writing that over the nth term, I'm going to basically do a copy dot flop. I'm going to write times the reciprocal of the nth term, so that would be n factorial over 2 to the n. Okay, so let's focus for just a moment on the 2 to the n plus 1 and the 2 to the n. We've got to do a little bit of work here. So if I have a base with a power divided by the same base with a power, what I do is I actually subtract my exponents. And so the way that that would look here, of course, is 2 to the n plus 1 times divided by 2 to the n. Subtracting those exponents, n plus 1 minus n, I just get 1. So the numerator ends up just being 2 to the first. The factorials are a little more complicated. N plus 1 factorial is actually n plus 1 times n factorial. And so what we would see here is that this n factorial and this n factorial would cancel, and that would leave us with simply n plus 1. Okay, and then looking at this as I try to apply the limit as n goes to infinity, the numerator is held constant and the denominator is increasing without bound, therefore the value of the fraction is approaching 0. And of course 0 is less than 1, so you'd say therefore the series converges. By the ratio test. Okay, so there is example number 1. Let's take a look at example number 2. All right, in example number 2, we're going to set up the same ratio. So limit as n goes to infinity of, so we're going to write n plus 1 in place of all the n's. That's going to be n plus 1 squared. And then 2, and so it's going to be n plus 1 plus 1, so it's really just going to be 2 to the n plus 2 over 3 to the n plus 1. And like before, I'm just going to multiply by the reciprocal of the nth term. So that's going to be 3 to the n over n squared 2 to the n plus 1. So like before, we got a little bit of work to do. So looking, there's no factorials here. Looking at my 3's, my base of 3, like before, if I'm dividing like bases, I subtract my exponents. And so at this time, though, we're going to end up with just a 3 in the denominator instead of the numerator, right? Because the plus 1 is down there. And then with the 2's, I've got 2 to the n plus 2, 2 to the n plus 1. So the numerator actually has an extra 2. So it's going to be 2 to the first in the top. So far 2/3. And then I've got n plus 1 squared, n squared. If we wanted to, we could rewrite that just a little bit. I don't think we have to, but let's do it just to hopefully make things as clear as possible. This would end up being the limit as n goes to infinity. We'd have 2/3 times, it's going to be n plus 1 over n, the whole thing squared. Okay, so of course the limit as n goes to infinity only applies to things that have n's in them. So when I look at that n plus 1 over n quantity squared, I could use L'Hopital's rule here. I could FOIL this thing out. I could do a number of things. I could use the old pre-calc trick. But no matter what we use, what we're going to end up with is we're going to end up with that that second term going to 1. And 2/3 times 1, of course, is just 2/3. And, of course, 2/3 is less than 1. So we would say, therefore, the series converges. And I just used the ratio test. Okay, so I hope you're getting the hang of that. Let's take a look at example number 3. Again, as always, feel free to stop the video, pause it, and see if you can work on the problem on your own, and then check and see if we agree. So here we go, number 3. Limit as n goes to infinity, and it's going to be n plus 1 to the n plus 1 over n plus 1 factorial times the reciprocal of the nth term. So as we look to do a little manipulation here, we get limit as n goes to infinity. The n factorial and the n plus 1 factorial will cancel similarly to what we did before. N plus 1 factorial is really just n plus 1 times n factorial. So that cancels with that. So I'm just going to end up with n plus 1 to the n plus 1 over n plus 1 times n to the n. So we got a little more canceling we could do here with the n plus 1s. And this is to the first, so I could just subtract my exponents again. So that would give me the limit as n goes to infinity of n plus 1 to the n over n to the n. So this one takes a little turn for the surprising here in a second. I could combine these two expressions of my fraction as n plus 1 over n all to the n. And then to get it into a form that some of you might have seen before, although I don't know, it could be written, of course, as 1 plus 1 over n to the n. So amazingly enough, the limit as n goes to infinity of 1 plus 1 over n to the n is e. And e is bigger than 1. Therefore, the series diverges. And that is the ratio test. I don't know that I would expect you to pull that out of your hat, the whole E thing there, but I think you can probably see that the resulting number is going to be bigger than 1. Okay, and then finally we get to number 4. We are going to look at this. Of course, this is an alternating series, but with the ratio test with those absolute values, they essentially cancel out that alternating piece. So the setup here looked like this. Limit as n goes to infinity of absolute value, and it's going to be the square root of n plus 1 over n plus 1 plus 1, so that's just n plus 2, times the reciprocal of the nth term, n plus 1 over root n. Here I'm going to just do a little bit of manipulation. So it's going to be limit as n goes to infinity. I'm going to write the radicals over each other, and then the other factors over each other. And I want to encourage you to remember that the limit of a product is equal to the product of the two limits. So when I look at just this left piece over here, and I think, all right, limit as n goes to infinity. You know what? I guess I could probably rewrite this a little bit differently. Let's go with this. Limit as n goes to infinity. Absolute value would be square root of n plus 1 over n times n plus 1 over n plus 2. Could write it that way. But again, I encourage you to remember that you know, as we go through the limits here, if we take the individual limits, we can just multiply the results and get our answer. So thinking about degrees, thinking about L'Hopital's rule, thinking about the pre-calc trick, the limit as n goes to infinity of n plus 1 over n is 1, and the limit of n plus 1 over n plus 2 as n goes to infinity is also 1. So I end up getting 1. And so the ratio test is inconclusive. And what we'd want to do then in that case is we would actually go back and use the alternating series test, and the alternating series test would show that the terms do decrease in absolute value to 0, and it is an alternating series, and so we would end up with a converging series. It would be conditionally convergent, but the alternating series would be convergent. Okay, that is the ratio test.